around another star. And as Christian likes to joke, that's more planets than the two current ground-based experiments, SPHERE and GPI, have managed to find between them. So that's quite an impressive yield. Christian did his bachelor's in physics at the University of Montreal, studying, I think, globular clusters or something that's not planetary. And then he wisened up and started doing exoplanets for his PhD and started doing high contrast imaging. And then did a postdoc, Lawrence Berkeley? No, which is
Lawrence Livermore National Lab at Denver.
It was one of the Lawrences. So I guess that's when Bruce McIntosh was still out there before he moved to Stanford. So he postdoc there, was somehow managed to be not only lead the HRD 799 paper that discovered, I guess, the first 3 planets in that system, but also was a co-author on the famous Fomalhaut, the Eye of Sauron planetary system. And that came out in the same issue of Science, I believe. So that was kind of a fantastic year, and as a result, won some impressive medals and awards. And there you have it. So without further ado, take it away, Christian.
Thank you, Nick. So I'll start sharing my screen, see that works. Okay. Can you guys see that?
Looks good from here, Christian.
Okay, so you're seeing my slide, not just me. Okay, so exoplanet imaging. So the last couple of talks, I believe, were mostly about the solar system. So now we're moving away from the solar system into the realm of the nearby stars and to try to directly image other planets and characterize them. So like Nick said, one of the famous discoveries, HRD 799, is actually the only multi-planet system that has been directly imaged to date, which is kind of worrying in some way, but I'll get to that later in the talk. So our solar system. So before 1992 to 1995, depending on who you talk to, the solar system was pretty much unique. So the planets orbiting other stars were on the realm of science fiction. So people need to watch movies to figure out what planets were out there. But now, since 1995, we actually started getting a very nice picture of what's going on, and what kind of planets and solar system, or planetary system that nature tend to form, and figure out if we're unique and how common are rocky planets, and if the architecture of our own solar system is typical compared to other solar systems. So how do planets form? So I'll go around that fairly quickly since I want to concentrate on direct imaging during the talk. So basically you start with a big ball of gas and dust, and it collapses into some kind of planetary disk, and out of that you form planets. How to form planet? There's roughly 2 big theories that can explain planet formation. We don't know if the 2 are ongoing in nature, or if one is more favored than the others. But one is called a co-accretion on the left, where you basically just start from small dust particles and you go into pebbles, and then pebbles into bigger objects, to rock, to kilometer size, into roughly a 10 Earth mass core. And if you happen to form that 10 Earth mass core fairly quickly, you can have a runaway accretion and have a big gas giant planet. And on the right is the disk fragmentation scenario, where you have your planetary disk, and basically you just collapse the dust and gas into a big giant planets. So the prediction of these 2 models actually differ quite a bit, and the realms of where they actually operate is different. So the co-accretion scenario, you tend to have a rocky core and with a big gas envelope for a gas giant planet. While smaller rocky planet, you have still a core and then a thinner atmosphere where life could develop if you have the right condition. While on the gas fragmentation scenario, you basically just have a planet with no core. And one of the biggest prediction of these is when you form planet by the co-accretion scenario, you tend to have a lot of shocks, which dissipate a lot of the energy. While here in the disk fragmentation scenario, the planets kind of form fairly quickly, and you conserve a lot of the initial energy of the collapse of the gas and dust into the planet. So these planets tend to be other than their counterpart formed by co-accretion. When you see a planet with a given age, let's say 1 billion years, planet formed by this fragmentation will tend to be brighter or more luminous than planet formed by co-accretion. So the talk I'll go very quickly about direct imaging, how it works, the first generation surveys, like the GDPS with David Lafreniere in Montreal, the IDPS and then other surveys, the current ongoing surveys with GPI and the future of the field. So we're trying to directly image and characterize habitable planet or temperate planets around the nearest stars. So why direct imaging? Well, first of all, direct imaging, you produce nice picture, which is what I like. If you compare to other technique, planets are basically points on a graph, which is very exciting. There's very cool science that's coming out of that. But I like the fact that you can actually point the telescope and look at the point source, like the H8799 planet, and see these planets moving. You can do spectroscopy, photometry. You can learn quite a bit about the planets, and sometimes in ways that are different than other planets, like radial velocity, macro lensing, astrometry, or transits. The discovery space is also quite different, so they actually don't overlap. Transit, so this is a separation and planet mass graph, and all the different color regions are where typically observing technique concentrate on due to various biases that could be, like, for example, imaging, where you need a big telescope to resolve the system, and at some point you just don't have big enough telescope, so just actually cut your ability to find closer in planet. And then it's a sensitivity issue that you can't go lower in mass because the planets are just too dim. So here in imaging, we're actually seeing usually the thermal emission. With the current technologies, we're seeing the thermal emission of the planet. So it needs to be emitting light. If the planet is too low mass, it's not enough light for us to be able to detect these. While transit, you usually focus on nearest planets that are higher mass from the ground and lower mass from space, like Kepler, etc. So all these techniques are studying and finding planets in the different regime of mass and separation around stars. So they all give us a more complete picture of what's happening and how nature is producing planets around other stars. So all the techniques are needed in some way to get the complete pictures. So the advantages of direct imaging, well, first of all, you get the direct detection. So you're actually seeing light from the planet, which allow you to do a more detailed characterization of the atmosphere. You can do photometry, spectroscopy, learn about the various parameter of the atmosphere, the composition, the effective temperature, the surface gravity. If there's any non-equilibrium chemistry that's ongoing, etc. If you can see clouds, like if you do a time-dependent analysis, Nick has some very nice paper about how to do this on rocky planets. But if you go down, like I said, for the more massive planets, you can see clouds. There's a very nice paper that came out by Daniela Pai a couple of weeks ago that it was discussed during the Exoclips meeting, where you could see gaps of clouds moving around the surface of brown dwarfs or planets. But if you go down to smaller rocky planets, you can see season clouds. You can map the surface of these planets and figure out if there's even continents, etc. You can do astrometry, you can fit orbit, you can track the planet moving around the star, which sometimes can complement other technique. Like if you find the same planet by direct imaging with radial velocity, you get a dynamical mass of the object, rather than a model-dependent mass. So one of the issues with direct imaging is we're seeing the total emitted light. You don't get the radius, you don't get the mass of the planet. So you need to derive these using evolution models, unless you can find that planet with another technique to complement. So how is this a resolution challenge? So if you take the solar system, so the Sun to Jupiter separation is 5 AU, and you put the system at 1 parsec, the angular separation between the two stars is 5 parsec. So here I add a resolution limit of different size of telescope. So if you have a 2 centimeter telescope at 1.6 micron in the infrared, you can resolve objects that are 16 arcsecond apart or more. So if you want to see the solar system at 1 parsec, you at least need a 10 centimeter telescope to be able to resolve that system. But you don't have any star to look at. There are no stars inside 1 parsec. Alpha Centauri is at 1.2 parsec. So there's no star to look at. If you go to 10 parsec, you now have 200 stars to look at. But now this angular separation between the sun and the Jupiter goes down to half an arc second. So you need now a meteor-sized telescope to be able to do your science. But 200 stars is actually not a lot. And actually, most of these are M dwarf, which are tiny, very red star, which give you more complication to be able to find these planets. And if you go up to 100 parsec, which is still in the solar neighborhood, you now have hundreds of thousands of stars to look at, but the angular separation between the sun and Jupiter is 0.05 arc second. And you now need 10 meter class telescope to be able to do your science. So if you want the biggest enough star sample to cherry pick the right star to look for the planet, you need to do the science on 10 meter class telescope or bigger. So this is a reason why it took so long for direct imaging to get into gear and start finding these systems that are at solar system scale, is we needed to wait for this 10 meter class telescope. So if you look at the Milky Way, you see the little round circle here on the sun. This is pretty much the volume where we're actually looking to directly image planets. So there's still quite a bit of space to cover. So we need larger and larger telescope to be able to expand our graphs in space and find more planets. The second challenge is the contrast challenge. So stars burn hydrogen. So after a million of years, roughly the sun doesn't change intensities until it evolves from the main sequence. But planets don't burn anything besides maybe deuterium for a short amount of time. So when a planet is very young, it's very bright, but as it gets older, it actually gets very dim. So if you catch a system that's billion of years old, the planets are so cold, they're so cool that they don't emit a lot of thermal emission. So it makes them very hard to see against a star. While if you find a system that's very young, the planets are still very warm from their recent formation. They still emit quite a bit of energy. They're 1,000 degree Kelvin or warmer, and they are much easier to see against the glare of the central star. So just to give you an idea, so this is a luminosity and age plot. So planets start here when you're on the top, near the top of this diagram, you're very bright. If you go down, you're dim. If you're on the left, you're young. If you're on the right side, you're old. So planets are the blue region here. There are different cooling tracks of planets of different masses, and this is all the known planets to date from the Bowler 2016 paper. So when you're very young, they're very bright, and as you age, the planets go dimmer and dimmer. So you start from a 10 to minus 4, which is 10,000 to 1 contrast for this line. And after billion of years, you go down to 10 to minus 7. So they are 1,000 times fainter in your images, and they're much harder to detect. So if you want to do direct imaging, you want to have very nearby star because you want to be able to resolve the system very easily with your 10 meter class telescope, and you want young star because you want to catch the planet when they are very bright, when they're very warm, and it make it easier to see against the glare. So they give you a more realistic or more down-to-earth example. If you consider the amount of energy coming out from the star as Mount Everest, if you're looking for a young Jupiter, you're looking for a football field size object lost on Mount Everest, which is hard, but this is like a 10 kilometer high mountain, and you're looking for a 700 meter high object. And this is your young gas giant like Jupiter, but probably around 1,000 or 1,500 Kelvin object. If you're looking for old 5 giga-year-old Jupiter, you're looking for a baseball lost on Mount Everest, which is getting harder and harder. And if you're looking for a tiny rocky planet like Earth, you're looking for this little red spider that walks on your leaves in the summer. So the challenge is quite impressive. So that's a reason why direct imaging is currently focusing with current technologies and 10-meter telescope at finding these young gas Jupiter. And until we have bigger telescope and more advanced instrumentation, can we go down to the reflected light of old Jupiter all the way down to a small rocky planet. So the contrast is roughly 10 to the 10 contrast, and here is roughly 10 to the 5, 6-ish contrast. So 100,000 to 1 to 10 billion to 1 contrast for a rocky planet. So how do we know that what we just find an object? The problem with direct imaging is you don't see the third dimension. So if you're looking at a star that's blue here, and you see an object beside it, you don't know if the object from a single image, a single band, if the object is actually orbiting the star or if it's a distant background star. So let's see, this is a very far, far away background star, what you see here in the image. And on the bottom here, you have another object. You don't know if it's close to the star that you're trying to image, if it's a planet orbiting that object, or if it's a very distant, far away star. So the technique that we're using to do that is what we call multi-epoch observation. So if that star is in the background, so far, far away, if you take a couple of images that are acquired several months apart, since all our stars are nearby to the sun, they actually move relative to the sun and relative to the background star. So as you're tracking the star, you see that the two objects in the background, they're moving together and they're not moving with the nearby star. So that's a proper motion analysis that tells you that this object right here is actually not in orbit around that star, but it's a far away distant star. Well, if this is actually an object that's orbiting this little object, it would actually move together in time. So this is how we actually can differ an object very easily that doesn't have any any hypothesis. It's a very clear-cut proof that the object that's red, that's beside this object in your image, is actually orbiting the blue star. And now with the technology. So talk about resolution, that you need a 10-meter telescope to diffract light. You need a very young star to be able to see your the planet more easily because they're still quite warm from their recent formation. But then most of this science is happening on the ground, and the ground has a very turbulent atmosphere. We need the atmosphere to breathe, which is useful, but for astronomy, it produces turbulence. So object, even if you have a 10-meter telescope, if you just put your camera there and you start taking pictures, you're going to have a big potato images, so very blurry images, and it would actually give you the resolution of a 20 to 30 centimeter telescope. Even if you have the light gathering power of a 10-meter telescope, your resolution is limited by the atmosphere to a 10 centimeter to 10 to 30 centimeter telescope, which is a big problem. So people in the 60s have been thinking about how to use ways to compensate the turbulence coming from our air. Originally was designed to take images and spectroscopy of satellites, like Russian satellites. But astronomy quickly saw the potential of developing this technology called adaptive optics, where you can take the light of your star that you're trying to take an image of, and you use a scheme, what we call a wavefront sensor, and some very fast computer, and a little mirror that has a membrane with little actuator that you can deform at the kilohertz speed, and you can compensate the effect of the atmosphere and have very sharp diffracted limited images. So basically this system, if it gets enough light, if your star is bright enough through the atmosphere, it can give you back images almost as you were in space. So the images are diffracted limited and you have the full resolution power of your 10-meter telescope. So this is an example here with the galaxy without adaptive optics. So you see it's limited by the atmosphere, it's very blurry. And with adaptive optics, it gives you very, very sharp images where you can see digital stars, star-forming region, etc., spiral arms, like you were in space. So this is a technique that was developed in the mid-1990s or early 1990s, and keep getting better and better with new ways of sensing the aberration, turbulence from the atmosphere, and give you very sharp images. So once you close the adaptive optic loop and you take an images, the star will look like this. So you're not out of the wood yet. So it's not like you just take a picture and you see the planet. If you have your diffracted limited images coming from your instrument, you're going to have a sea of what we call speckle. So all your optics, now you get rid of the atmosphere, you get rid of everything that's random, that's moving at high speed and high altitude above your telescope. Now you're left with all the imperfection in your telescope and optics. All these little bumps and deviation from the perfect parabola of your mirrors produce all these little streaks of lights. And these are small interference secondary maximum that comes from the interference of your wavefront going through your optics. And they all look, basically they're noise. that mimics the light of your planets. So to be able to find your very tiny, faint planet, you need to find ways to get rid of this noise. And it's actually not easy. So it's like you're asking these guys, who's the planet, and you're expecting a good answer. It's actually not obvious. You need to figure out ways to decouple or ways to remove this pattern to be able to see your planet. So when I did my PhD student, I was a PhD at the University of Montreal. We came up with a solution with René Racine and Daniel Nadeau and René Doyon and others. It was to simply split the beam in three and take three simultaneous images at three color. The instrument was called Trident back in 2001. So we designed this during my PhD thesis, assembled it, went to CFHT, took images. And we also took images in the of Saturn, and we selected the near-infrared bands where there was methane. So in one band, stuff that has methane were very bright, and then we put two bands inside the methane absorption band, and you could see the Saturn, the planet, disappearing in the methane because Saturn has methane, but the ring, giving its only reflected light, stays the same brightness no matter the band. So the idea was to combine these images to get rid of the speckle noise coming from the star, but to retain the light of planet that has methane. So the planet, after this combination and subtraction of images, the planet having methane would survive the subtraction, but everything coming from the star that doesn't have methane would be subtracted. So on the left, this was the simulation I did back when I was a grad student, showing that the original images and then showing the speckle noise and then some pair of subtraction, and then you see that you gain in contrast by subtracting images. But what we got was actually a lot more words than what we were expecting. So these are real images from Trident back in 2001, and you see that we were supposed to get something really good to be able to find these little planets, while what we got is a huge mess. And that's where we realized that non-common path aberration, so when we split the beam, these surfaces need to be extremely good or they generate non-common path aberration. So finding ways so after thinking about this problem, I realized a different technique that we could use on these 10-meter telescope is called angular differential imaging. And this technique is now widely used by pretty much everyone doing high contrast imaging right now on 10-meter class telescope. Is instead of splitting the beam in multicolor, what we now use is only one band, but we use the fact that all the 8-meter telescope are designed as an altitude azimuth mount telescope. And they do this, so they rotate in azimuth and altitude. And they do this to basically save costs because it's easier to build a telescope like this than one that has an equatorial mount that points toward the celestial pole, especially if you're near the equator because the telescope is almost horizontal, which is making it super hard. And what happens if you have an altitude azimuth telescope and you're tracking the sky is, as a grad student, I realized that if you keep tracking a star in the sky, all your optical, your telescope, your instrument, once you remove the turbulence from the atmosphere, they're all going to stay aligned with time. But since you're tracking the sky with an altitude azimuth telescope, the field of view is actually rotating with time. So usually telescope have built-in rotator that rotate your instrument to compensate that rotation. So my original idea was simply to unplug a rotator at Gemini North, and then we just took images every 30 seconds or every 60 seconds for an hour. And since everything stays aligned with time, all the speckles stay roughly static, but the planet's going to be, if there's any planet in the field, they're going to be rotating with time. So that's an example. So this is a bunch of 20-second exposure with Keck. This is the subtractor. So you can devise algorithm, like David has a very nice least-square based algorithm to reject the noise from the star. And this is the combined image. As you take images with time, you just collapse these images and co-add them with time. So you can already, if you have a very good eye, you can actually see there's a point source there. So you can take a quick look. You see these planets revolving around the star. And this is only due to Earth's rotation. So you start over here. So you see the combined images. You were only seeing 1 and 2 images after post-processing the images. But after collapsing, you see there's actually 4 objects. And this is HRD 799 over an hour worth of observation at Keck, where you see all 4 planets appearing at K-band. So this is really a revolution in the field because it's the first time that we finally has an observation technique that would guarantee you a square root of n gain of contrast as you keep integrating. So the longer you integrate, the deeper you get and the lower mass planet that you can detect. Originally, people before this technique, they were just point and shooting a star, but this speckle noise was not averaging. So you take a 30-second exposure, a 1 hour exposure, and you would get the exact same result. So the images would not get better in time. But this observing strategy would guarantee you a gain of almost 200 in contrast. So this is really a revolution in the field. So we developed this with David Lafreniere in Montreal, and we came up, like I said, with better algorithm and roughly give you a gain of 200 in speckle suppression. So before 2014, we were all using general use adaptive optics system, using this angular differential imaging mostly. Some people were using SDI, but they were quite limited. Many hundred stars have been surveyed by many teams, including David Lafreniere with GDPS, Bette Biller in Arizona, and VLT, Chauvin. There's probably roughly 10-ish campaigns that have used 10-meter telescope for, I would estimate, around more than 2,000 hours of telescope time on 10-meter time. It's probably worth around $20 million worth of telescope time. And one of the discoveries that we made is the HR-799 system out of that. So HR-799 is a star in the Pegasus constellation. So you can get out tonight and take a look at it if you have small binocular. It's a magnitude roughly 6. So you need binocular to see it. You can't see it by your naked eye, but with your eyes. It's actually located very close to 51 Peg. First planet discovered by radial velocity back in 1995. And there's a nice anecdote is actually Jeff Marcy, after the discovery of 51 Peg, they already had data and they were trying to find planets orbiting at water separation around 51 Peg. So they took images with the Keck telescope and they used HR-799 as a reference star. So they took images of that field and images of HR-799 to try to subtract the PSF to find 51 Peg. So thank God at the time the Keck did not have any adaptive optic system. So that's the reason why they didn't saw the planet of HR-799. But if that observation would have occurred a couple of years later, they would actually find a HR-799 planet while trying to find planet around 51 Peg, which is crazy. So the star is 39 parsecs away, or roughly 130 light years. The system is fairly young. It's actually now believed to be more 30 million years in the Columba Star Association. So star sometimes are part of cluster of young stars that we believe they move in the same way in the galaxy, and we believe that they're formed roughly at the same time. So in some of the membership, the cluster membership is roughly known by some star in the cluster that are well-known age by other techniques. So we believe that HR-8799 is roughly 30 million years. It's 50% more massive than the sun, and it's warmer as well. It's around 7,000 Kelvin. So it's 5 times as luminous as the sun. So some people ask me how big in the sky is the HR-799 system. So if you take the original image back in 2008, so the distance of Neptune is roughly the distance of the planet C. So if you take your hair and you put it at arm's length and you put it in front of the system, this is roughly your hair and the size of the system. So you really need a big telescope to be able to see this. So on the left, it was to give you an idea of what the planets look like on Voyager spacecraft. That's at the time was at 43 astronomical unit with the 18 centimeter telescope. Planets of our solar system are just point sources. For HR-799, it's instead of 43 AU, it's 8 million AU away. But with a 10-meter telescope, they give you a similar picture of planets orbiting the system. So we know they orbit around counterclockwise, so they're 14 AU to 68 AU. They're really warm. So instead of looking like Jupiter with very cold ammonium clouds and other methane and etc. CO inside the atmosphere, they look more like a much warmer version. So Jupiter is around 140 Kelvin, if I remember correctly. The H.R. 799 planets are closer to 800 to 1,000 Kelvin. So they're much, much warmer version of Jupiter. So they probably partially close. They probably have a lot of dust particle, and they're slowly sinking in the atmosphere. So we do have trace of methane that's detected for planet H.R. 799b, while the others are just too hard for the detection. They're probably too warm yet to be able to see clear methane. So I talked about at the beginning about two formation models. So when we found the fourth planet in the system, H.R. 799e, which got interesting is the core. People thought at the beginning that the planet are probably a form like B, C, and D by the disfragmentation scenario, which usually work at water separation because you need a very cold disk to allow for the fragmentation to occur, which was fine. But what happened is at some point we found planet E at 15 AU, and at that separation, the disk is thought to be too warm for the planet to form by the disfragmentation scenario. So it would need to form by core accretion. But the problem is the planet B, C, and D are thought to be too far away from the star that there's not enough collision happening to be able to form this planet by core accretion. So you end up with a system that there's no planet formation mechanism that can explain the existence of these four planets simultaneously. So or some has formed in one way and others has formed another way, or the planet that all formed closer in and then migrated outward, or formed further out and migrated inward. But there's something else that has happened to this system. They probably did not form at their current location, or there's something we don't yet understand clearly about how planets form, which is probably true as well. So one thing is interesting is if you scale the position of the planets with luminosity. So if you take the solar system, that there's an asteroid belt and there's a Kuiper belt and then the gas giant, Neptune, Uranus, Saturn, and Jupiter. So if you scale the planet's position with luminosity, H.R. 799 being 5 times brighter than than the sun, you end up that the position of the planets are actually quite close to Jupiter, Saturn, Uranus, and Neptune. And we know from the infrared excess, from the infrared, for thermal infrared analysis, that the system does have a Kuiper belt as well, and a Kuiper belt like an asteroid belt and a Kuiper belt, similar to the solar system, and the planets are located at roughly the same position in luminosity to the planet of our own solar system. So even if it's a much bigger system that goes up to 68 AU in projection space, than the solar system planet in terms of luminosity and local, not local parameters, but the local conditions of how the planet formed were actually similar to the solar system. So some time ago, a couple of months ago, Jason Wang, a grad student in Berkeley, and Jason was having fun with the interpolation method to do some kind of morphing between epoch to make better movies, because I was presenting these movies by just blinking images of the system for the last decade, basically. But Jason had fun with morphing technologies to make better movies. So this is what the orbital motion of H.R. 799 planets look like. So you can see Kepler motion, counterclockwise orbit. You see planet B moving slowly, planet E moving faster. So you really see Kepler laws in action for planets orbiting another system. And the fun part is it took us an afternoon to do this movie because people on our Facebook exoplanet imaging were asking for a movie to show people from the public or the students about Kepler laws and around other solar systems. So we made this in an afternoon, and then Jason put that on his YouTube channel or something, and we got 1 million views in a matter of 2 days, which is crazy. It was trending on Reddit, so we had quite a bit of fun. But it's just amazing sometimes a 2 or 3 hour worth of work, and it just exploded into this public view. We did have some very nice, I'm going to try to accelerate here, nice follow-up observation using OSIRIS, an instrument at Keck, an integral field spectrograph. We got some R5000 images, R 5000 resolution spectroscopy of H3799c. You can see individual lines. So we managed to estimate the CTO ratio of the atmosphere of the planet. There's, like I said, clear CO detection. There's also water line detection. So it's probably the highest SNR, highest resolution spectrum of an exoplanet that ever been acquired is on H3799. Like I said, the CO2 ratio is slightly supersolar. The lack of oxygen, which might be a hint that it formed by co-accretion, but it's still quite preliminary in terms of conclusion, but a very nice result by our team. And we're also trying to derive the full orbit. So they orbit in 50 to almost 200 years for the furthest planet. So it takes quite a while to derive a very stable orbit. So we're still seeing some weird effects, so we know that they're probably coplanar. They're mostly in resonances from 1, 2, 4. It's probably a reason why the system is stable. I won't go into that details because that's an hour talk as well to go in detail about all the analysis on H3799. There's probably more than 1,000 papers citing H3799 right now. But yeah, the interesting thing is the inclination is around 30 to 40 degrees. So we knew that at the beginning that it was low inclination. Eccentricities are very low, so they're mostly circular, and like I said, mostly in resonances. So the first generation survey, this is the planet they found. So I guess it's a bias. I could spend an hour probably on each of these detection. Beta Pic is the detection done by Anne-Marie Lagrange, a very young 10 million year old star with a well-known edge on disk, and they found a 10-ish Jupiter mass object in the system. You can actually see it moving around, which is very fun. Fomalhaut B, which we're not sure what it is. Again, that's another hour talk. We're not sure if it's a debris from a collision or a real planet seen in reflected light. J1609, a planet by Ray J and David Lafreniere. 10-ish Jupiter mass object is again GJ504b. Anyway, so there's quite a few discoveries from the first generation survey up to 2014. An interesting one is Kappa NB, which is a super Jupiter, like a 15 Jupiter mass object, more in the brown dwarf regime, but they did manage to get a beer name out of it, so I think they won part of the competition of these planets. So that's pretty much the picture right now in late 2016 about all the blue object being planets. Some are orbiting brown dwarfs, so we're not sure if we should call these planets, but that's the subject of another talk. There's a lot of objects near the transition between what we call the brown dwarf and the exoplanet at around 13 Jupiter mass. That's again very interesting. That's about it. In terms of statistics, we know that there are a couple of papers that came out and they're saying statistics. We know that planets are rare. So if you take our IDPS survey, a survey that's been ongoing since 2007 to 2016 when we published the paper, we observed almost 200 sequences. Found a lot of background objects. So this is how you track with multiple epoch all your object. We found binaries. These are all the sources that have been detected in our images. So most of these are background, of course, except H3799. So we can derive, if you use models, you can come up with your probability of detection of different masses. So if you take a 13 Jupiter mass object for 256 stars at 100 AU, you get 90% chance roughly of detecting it. And for a 1 Jupiter mass object at 100 AU, you get the 10% chance of seeing it. Or only 10% of the star could have seen it. Is another way to see it. So this is what we're using to derive statistics. So it's really model dependent. But we came up, if you split this, so one thing we were wondering if more massive stars tend to form more massive planet, because we found H3799 and lower mass star, we didn't find anything. So if you look at the statistics for higher mass stars, so B, A, and F star, we find that's around 4% of star has these kind of planet like H3799, and for lower mass star, we can only put upper limits. But the upper limit is less than, less than 2 to 3%. So we don't yet have enough sampling or statistics to really give a very strong argument that more massive star Yeah, less than 3%. Ours is 4% minus 2.5 to plus 7.4. So there's probably a trend, but it's not enough, strong enough. The statistical method is strong enough to say for sure that higher mass stars do form more massive gas giant planet at wide separation between 20 and 380. Okay, for the next 5 minutes, GPI, a new instrument for Gemini South, was supposed to be 2010. Okay, finally, the first slide was 2014. It's a state-of-the-art adaptive optics system, a chronograph similar to the technology to block the sun from space, or the moon if you saw the eclipse, to see the corona, and then an imaging spectrograph to take low-resolution spectroscopy of planets. So I'll skip that since we're getting tight on time. So it's a combination of adaptive optics system. There's a calibration unit that sadly doesn't work. A chronograph and an integral field spectrograph. So this is the instrument right there. This is the Gemini South Observatory, an 8.1 meter telescope. The instrument is right there. It's been operating since 2013. We have a 600 star campaign, almost 900 hours. It's roughly sometimes go up to 200 times better than previous generation of instrument. And so far we did 380 star. We have a pipeline to take these little spectra into data queues, process them, and be able to find planets automatically. So basically, we just sit down, take the data, and software is doing all the job. Like 200 times better. I'll skip that. There's also a polarimetry, so you can see the dust signature by polarization. So this is the backscattering of dust, like a cubicle-like disk, with light from the star backscattering toward us and being polarized. So you can look for polarized light in around stars. And so there's again, that's probably the most successful part of the instrument so far, is this detection and characterization. So that's a slide by Marshall Perrin, with showing several debris disks that have been found or imaged by GPI. Like I said, we have live telemetry, data reduction. So that's my version of the quick look that gives you, a bunch of statistics of contrast, how good is the images, and then several ways of processing the data, and then automatically find the planet and output a spectrum, pretty much ready for publication, which is pretty cool. First big discovery, 51 Area B. So the HRD799 were a very dusty and warm object. So a 51 Area is a cooler 700 Kelvin-ish object around a star that's 10 to 20 million years old. You can see here is a small movie. You can see the object became bright, so you can see it has methane in the atmosphere. It becomes bright at around 1.57 micron and then dim. We saw the object at the H band, J band, K band as well, and all the way to L prime. So we went back to Keck for a very good sequence at L prime using NERC2, and we saw the object would give you a more handle of analyzing the effective temperature of the planet. So roughly 20 million years now on the beta peak moving group, and around 14 astronomical units from the star. So I can skip that. We're starting fitting the orbits, so that's a 2-year-old paper, but we see it moving around the star. Again, at 40-ish degree inclination, but it's very well constrained. An interesting thing, so this is again a cooling track. 51 Area B is actually consistent with the formation scenario from the disk fragmentation, but all is so dim and so faint, it's actually consistent as well with some model of core accretion. We're not yet sure how it formed, but it's actually consistent with both models in terms of what they predict, which is interesting. We have spectroscopy, like I said, from J band to H and K band all the way to L prime, photometry. We observe beta peak. This is what was done with NACO at VLT a couple of years ago, and then GPI, the planet is like a candle. It's obvious in the images. The performance are so good that it's quite interesting. So one thing we're looking into if it will transit the star. It's actually transiting right now. So the big question is, will it cross the disk or miss the disk? From our analysis, it will actually not transit is only 0.5% probability of transiting in late 2017. So right now, but we believe that Hills field will transit. So if it had rings or moon, we might be able to see material around the planet. So a lot of people have campaigns in Antarctica right now and on space using small telescope to track the star brightness and see if we can see the planet or Hills field transit. We did HRD 799 as well. Very hard target for GPI because it's way north from Gemini South and we have some vibration issues. So not very easy. 9586, another object which we track, so I'm going to skip that. Master student Mara Johnson Grove was with me a year ago. She did a master, and we analyzed a high massive brown dwarf, low mass or object. So so people are publishing papers. It's pretty successful so far. Next 2 years, more disk, more planet, and more statistics on figure out the occurrence of giant planets that more than 10 years around stars. We're planning from upgrade in 2019 and going to north in 2020. Ben Girard, my student, is also on the line. Part of the steps is working at improving data processing for GPI, trying to combine also a reference star archive with multi-wavelength and angular definition imaging to try to optimize parameters. So that still work. We're also looking ways to upgrade GPI to do better by a factor 20 to 50. Depending on the brightness of the star. So the Ben could talk about that at some point. Future with TMT, bigger. If it goes to Hawaii or Canary Island, no matter, it's 3 times diameter, 10 times the flux. It has the potential to look for habitable planets. So this is the Nifrius instrument, give you an idea of the size of these instruments. The bigger the telescope, the bigger the instruments. It's the size of a small truck with optics that are 30 to 40 centimeter diameter, quite expensive. Some science case, you could do a higher resolution spectroscopy of known planet astrometry, time variability to look for clouds or surface features. You could even look for exomoon and habitable planets. Give you an idea, this is HRD 799 with Keck, with what we're expecting with GPI, but it's not as good as this for this reason with TMT. So this is planet E and D with TMT, and this is E and D with the 10-meter telescope. So the gain of resolution of diameter is quite impressive, allowing us to find much closer in planets around the nearest stars. So bigger telescopes are better. You could look for exomoons by looking at the RV or transits with a very good stable campaign. See weather on these planets with the higher SNR we'll be able to get with these 10-meter telescope. Like I said, exomoon, if you look for an Earth mass moon around a gas giant, the RV is around 10 meters per second with a period of a few days. So you could imagine if you have a very high resolution spectroscopy of a known planet and lots of lines and good models to extract the RV signal, you could look for an Earth-sized moon around gas giants. And very high, since we're going to have much higher SNR, you can start thinking again doing these transit surveys to find for these a few days where period moons around planets. One thing I'm been pushing is 10 micron imaging, so I'm almost done. I think I have maybe 3 minutes. It was 10 microns. Earth is actually it's the brightest object of the solar system at 10 microns. The contrast is, instead of a 10 to the 10 contrast in the visible, like if you're looking for a rocky planet in reflected light, is a 10 to the 10 contrast. But if you go to 10 micron, the contrast is around 10 to the 7. So it's 1,000 times easier to see a rocky planet at 10 micron than it is in the visible. And they are, of course, biomarkers like ozone, CH4, water, and CO2 that you can extract from spectroscopy. So we're designing an instrument to go to Gemini South for between 50 to 200 hours. It's a decent survey for one star for around Alpha Centauri, A and B. So if you put A under a chronograph, so the little dot of light right here, this is a copy of Earth at SNR around 4 after 50 to 200 hours. So 200 hours will be conservative here. And if you go to TMT, this is what you get around Alpha Cent. So assuming that TMT would go in the south or another ELT. So this is on Earth with the 100 hour of an ELT. You see Venus, you almost see Mars, and you could see a Jupiter at 1.3 parsec. So 10 micron and an ELT, you get a D to the 4 gain in efficiency. So you're much more sensitive than a 10-meter telescope. And for the nearest system, you will really be able to go down. For an Earth planet, you can actually see it at 3 sigma in less than an hour with an ELT. So there's a really big push for the 10 micron folks around the world to get this instrument on sky as quickly as possible once these 24 to 30 meter class telescope will be online. With a 30 meter telescope, so how many stars could you do at thermal infrared? You could do alpha Cent A and B. Epsilon Eridani, Procyon is a good one. 61 Cygni A and B. Epsilon Indi, Tau Ceti has a known RV planets around it. You'll be able to see these planets at thermal emission at 10 microns, and maybe Grumbridge as well, but it's getting at the limit of sensitivity for a 30 meter telescope. So roughly an 8 meter telescope cut here. So you can, with an 8 meter, you can only do alpha Cent A and B. With a 30 meter telescope, you can do all this, but it's still a resolution challenge because you're going to be working at 1 or 2 lambda over D for this system. But Tau Ceti is really one of the prime target. Procyon as well, Epsilon Eridani, and of course alpha Cent. But yeah, ELT is going to be quite exciting at 10 micron. We also have a version with Ben and I. We're working on a visible version of this, but that's still too early to discuss in meetings. But we're making some good progress. Conclusion: so direct imaging, first generation surveys are now over. We're now in the Sphere GPI second generation campaign, pushing down to 10 AU around star instead of 20 AU. We know that these gas giant planets are rare. Only a couple of percent of star has these gas giant planet that wide separation. We're looking into upgrading this instrument to go even deeper and toward another Earth in the near future. Thank you.
All right.